Welcome to this walkthrough on designing a 12-cell lithium-ion battery management system using Quickboards. In this video, we'll go step by step through the design process, from defining system requirements to building the schematic using modular, reusable Quickboards blocks. Let's get started. We'll start with an overview of what a BMS is, how it works, and where it's typically used. Next, we'll define a set of design requirements to guide our development process. From there, we'll create a high-level block diagram based on those specifications. Once the architecture is clear, we'll use the Quickboards schematic library to find ready-made design blocks for each section of the circuit. We'll then connect these blocks using hierarchical design to form the full BMS schematic. Finally, we'll wrap up with a summary of what we achieved and outline the next steps. A battery management system, or BMS, is an electronic control system that monitors and manages the operation of rechargeable batteries, typically lithium-ion, lithium polymer, or similar chemistries. Its main purpose is to ensure the battery pack operates safely, efficiently, and within its designed limits. A BMS measures individual cell voltages, monitors temperature and current, and balances cells to maintain consistent charge levels across the pack. It also provides protection by disconnecting the battery during overvoltage, undervoltage, overcurrent, or over-temperature conditions. Beyond protection, it enables accurate state of charge estimation, improves battery lifespan, and provides diagnostic data to the rest of the system. Battery management systems are used in a wide range of applications, from electric vehicles and energy storage systems to drones, robotics, and portable electronics. Next, we'll develop a set of requirements to guide our battery management system design. It needs to measure each cell's voltage and balance all 12 cells to maintain consistent charge levels. It must also measure the total pack current and monitor the temperature of each cell. To safely connect or disconnect the battery from the load, the BMS must control a relay driven by a dedicated relay driver circuit. For data acquisition, diagnostics, and system control, a microcontroller serves as the core of the design. And finally, to power all of these circuits, a stable power management stage is required. A high-level block diagram will guide us through the design of the battery management system. We'll start with the battery pack as the core of our system. Next, we'll include a cell measurement circuit to monitor individual cell voltages, a balancing circuit to equalize cell charge levels, and a temperature measurement circuit to track cell temperatures. On the positive output terminal of the pack, we'll add a current measurement circuit, followed by a mechanical relay that connects or disconnects the battery from the load. A relay driver circuit will energize the relay coil based on an input signal. To coordinate these subsystems, a microcontroller will handle data collection and system control. Finally, a power management block will supply stable power to all circuits across the BMS. To simplify and streamline our design process, we'll use the Quickboards schematic library, a collection of ready-made, proven circuit designs. The library includes schematic blocks for microcontrollers, sensors, power management, analog filters, signal acquisition, signal generation, and more. We'll select the schematic blocks that best match each section of our block diagram, import them into our project, and then make any necessary adjustments to meet our specific design requirements. For cell measurement and balancing, we'll use schematic block number 020052025, a power management block designed for cell voltage measurement and passive balancing control. On the right side of the schematic is the LTC6811 integrated circuit, responsible for measuring individual cell voltages and performing cell balancing. On the left is the LTC6820, which converts the standard SPI interface into isolated SPI communication. These two chips communicate through a pulse transformer, keeping the battery pack ground electrically isolated from the rest of the system ground. The LTC6811 measures cell voltages through pins C0 to C12 and controls cell balancing using pins S1 to S12. The second schematic within the power management block includes two key circuits, an RC filter for cell voltage measurement and a P-channel MOSFET used for cell balancing. During balancing, each cell is momentarily shorted through a 20 ohm resistor to dissipate excess charge. This resistor value can be adjusted higher or lower depending on the desired balancing current. Both circuits are repeated across all 12 cells and connect to the LTC6811 through the cell measurement pins C0 to C12 and the balancing control pins S1 to S12. Finally, the circuit interfaces with the battery pack using a standard Phoenix connector, as shown in the schematic. From the sensor blocks library, we've selected schematic block number 0402222024, a simple SMD temperature array designed for compact integration. In this design, we're assuming the battery pack is mounted directly on the PCB, allowing cell temperatures to be measured right on the board. However, in many real-world applications, the battery pack is physically separate from the BMS circuit. In those cases, NTC thermistors or thermocouples are typically attached to the battery cells, then connected to the BMS board through a cable and connector. From the sensor blocks library, we've selected a 150 amp bidirectional Hall effect current sensor for our design. The battery current flows through the IP plus and IP minus terminals, while the sensor outputs a voltage signal at V-out that is linearly proportional to the measured current. This allows accurate monitoring of both charging and discharging currents in the battery pack. To measure the temperature sensor outputs and the current sensor voltage, we'll need an analog-to-digital converter. Several ADC options are available in the Quickboards schematic library, and for this design we've selected a 10-bit successive approximation register, or SAR, ADC. This circuit block includes a 2.5-volt voltage regulator, which provides a stable reference voltage for accurate conversions. Sensor voltages are connected to inputs IN0 through IN7, while digital output data is communicated to the microcontroller via the SPI interface, using chip select, data in, data out, and clock pins. There are several power relay options available on DigiKey that satisfy our requirements. In this instance, a 12-volt single-pole, single-throw PCB relay is chosen. To drive the relay, we've selected schematic block number 0202222025, which features an array of 8 N-channel MOSFETs. In this design, one side of the relay's energizing coil is connected to 12 volts, while the other side is connected to the drain of MOSFET number 1. The gate input, labeled Input 1, will be controlled by the microcontroller to switch the relay on and off. There are several microcontroller options available in the Quickboards library. For this design, we've selected schematic block number 0100422024, a 16-bit Pixie-24 microcontroller. It offers ample flash memory, strong performance, and a rich set of peripherals and I/O pins, making it well suited to handle all monitoring and control tasks within the battery management system. The second schematic within the PIC24 block contains the microcontroller's peripheral circuits. This includes the in-circuit serial programming port, a 20 MHz crystal oscillator, a status LED, UART receive and transmit ports, and several decoupling capacitors for power stability. To power all the subcircuits, we've selected Power Management Schematic Block number 0200122024, which includes 6 buck converter channels. For this design, only the 3.3-volt and 5-volt converters are required to supply the necessary rails for the microcontroller, sensors, and communication circuits. To power the LTC6811 chip while maintaining ground isolation, we've selected Isolated Power Management Schematic Block number 0200322024. On the left side of the transformer, the circuit includes a switching regulator, input capacitor banks, and programming resistors. On the right side, it features a rectifier, output capacitors, and a 15-volt linear regulator. For our design, we can replace this linear regulator with the 5-volt buck converter from the previous schematic to better suit our voltage requirements. To finalize the battery management system schematic, we'll import each design block as a schematic sheet within a hierarchical project. We'll start with the power management block for cell measurement and balancing, followed by the microcontroller block. Next, we'll add the output MOSFET block for controlling two relays, one for the battery connection and another for the charging circuit. We'll then include the ADC block along with the current and temperature sensor blocks. Finally, the main power management block will be added to supply all circuits in the system. The voltage outputs from the temperature and current sensors are routed to the analog to digital converter. The battery and charge relay drivers are connected to two general-purpose I/O pins of the microcontroller, and to enable communication between the microcontroller, the LTC6811, and the ADC, a Serial Peripheral Interface, or SPI bus, is used. In this walkthrough, we started with a simple set of text-based requirements, defining what our battery management system needed to measure, control, and protect. From there, we translated those requirements into a high-level block diagram outlining each functional section of the system. Using the Quickboards schematic library, we quickly assembled a complete design by selecting proven, ready-to-use circuit blocks for each part of the BMS, including power management, sensing, control, and communication. In just a short time, we moved from concept to a full schematic, something that would traditionally take weeks or even months to build from scratch. Quickboards lets you focus on design intent instead of repetitive tasks, helping you accelerate development, reduce errors, and reach testing and validation faster. If you'd like to explore the Quickboards schematic library, visit quickboards.org to download and start using it in your own projects today. Your subscription directly supports the growth of the library, helping us expand the collection and bring even more ready-to-use designs to engineers like you.